Alright, so I was just checking to make sure that everybody could work the problems that we were assigned. So I'm going to go through the Matlab files first in this video. And so this is from problem 1 in week 13. And the two files are TGF example and Woodhoff 2. So this is from earlier example, right? So this is just showing us that we can use a linear classifier. Or a neural net as a classifier. So there's the one file. There's this other from our folder. And so now I just run the TGF example. I'll probably need to, maybe I'll just hit the run button. I'm thinking I may need to, oh, I didn't need to do that. So I did get an error though. What's the error? I was thinking I needed to, oh, I've got the confusion matrix that I need and Woodhoff. So I need to change a couple of things here. I thought that was Woodhoff 2 when I looked at that before. So let's take a look here. Yeah, that's Woodhoff 2, and that's Woodhoff 2, and oh, that's Woodhoff 1. Okay, so that's what it didn't like. So I'll change that. Go ahead and I'll leave it this way because it actually did run. Although for the confusion matrix, I didn't put the confusion matrix in this bundle. You'll remember where it is on the class website. Let me pause for a minute and locate it. Okay, so that was under April 14th, K-neural network, or K-nearest neighbor regression. It's the folder with the Matlab and Python files. So if you go to the classifier, it'll be there. So let me go ahead and I'll download that. Save link as. Save. Okay, and now I'll pause and get it back into Octave. Okay, so I pulled the confusion matrix file down here, and so let me put it into Octave. Good, and now let's run that again. Let me go ahead and clear everything out here. Okay, and now we can run that example again, hopefully without any errors. Hey, that looks good. Okay, so there's our error. Whoop. And so how do we do? I think that's our output. That's our file. That's our error. Where's our... Didn't we have a confusion matrix come out? Oh, right at the end. I guess I didn't print it out. So C. So there's our confusion matrix. Good. Of course, it's just 2, 2, 2. So that's not a big deal. Okay, so this was the example of using the linear classifier. So if you look in the Matlab code itself, right, basically the first half of this is just getting the data together. And so the main code doesn't start until line 27. And so really all you do for the linear neural net is you do the Woodhoff 2, right? And so that's the online training. Good. So yeah, let's go ahead and delete these files now, and we'll go to the next problem. And we'll just, so I'm just, it's easy to just delete these, and then it keeps the Octave Online open. And so then we'll go to our next problem in the file, and we'll go to the Matlab files. Oh, there's the confusion matrix. Okay, so this is going to take most of these files, I think. So this is the wine app and wine classification. This is a wine data classification example. So we are going to use diabetes. Well, I'll just go ahead and put that in there too. Okay, and then just upload all those files. Wine app 0 is the main application. So we'll go ahead and run that and make sure everything works. Okay, good. And we got a classifier, right, our confusion matrix right off the bat. So you'll notice here what the files are. So in line 3 and 4, we just load the data, scale it. Remember in that example we were talking about the wine, without the scaling we got really bad output. So keep that in mind. Line 7, 8, and 9 are just building the data. Line 11 is splitting the data into training and testing. And here 13 is the main line here. 13, where it calls RBF OLS. That is the main, that is the orthogonal least squares. And so if you take a look at that, it's a pretty big file, but it's really just all the linear algebra that we were talking about in the theory for OLS. So initially it's just doing some sizing. Notice line 32 here. That is MATLAB's default for the determining the spread of the neural nets. And then this RADBAS1 here is just applying the transfer function phi, which is our exponential function, to the distance matrix. And that distance matrix is multiplied by the spread. And then some of these are just going to be used for some distances. So this p squared here is pp, and that's the sum of p dot times p. Remember, that's just going to be p squared, element-wise p squared. And then when you sum, it goes down all the columns, so you end up with a row. And then when you transpose that, it becomes a column. So this is a column of all the column norms. It should be a row, but then it was flipped over into a column. Similarly for D. D is actually the targets, and then D squared here is the sum of the norms. Good. And then line 41 is kind of probably the most important one in this OLS. That's because the E here, I don't know why they call it errors. These are the cosine squareds between the set of vectors in your design matrix phi and the output targets D. Okay, and those are we'll show that in the we actually show this in the exercises. Okay, and then the rest of this is really just if you look down here, we're really just either putting elements into a vector or pulling elements out of a vector. And so that's all that's all that this is. This is just some bookkeeping, because the bookkeeping keeps track of which vectors are being used. Okay, and then yeah, we don't need to read the whole thing, but you might take a look at it. It's a very interesting algorithm, and actually if you're interested in MATLAB programming, this is a really nice piece of code to take a look at, because this is MATLAB's way of training the RBF. Okay, I'm just rewriting a lot of it for us, but this is basically at the heart of MATLAB's own code. So this is, so you can think of this as more of a professional coding. Good. Of course, this is a little bit of old code too, but it's good to look at. And so this is using, again, orthogonal least squares to pull off the centers. And notice that what's coming out is actually a data structure with all the stuff that we have in it. So the set of centers is in netparams.c. The set of weights is netparams.w. The set of the bias vector is netparams.b. And then the spread constant is netparams.spr. And so this is a handy way of collecting all of the different parameters that are in the RBF. Okay, so notice that the next value is going to be, or the next function is Rbf Predict. And so what do we need for Rbf Predict? The net params that we just constructed. Notice that that's the very first thing that's done here, right, is to go through all the parameters and put them out into, or break them out so that we can use them. And then, yeah, then that's followed by the data that you want to predict on. And so this is giving you the predicted output for the x being input. And so you'll see the same helper functions down here that we had over there. Very good. All right. And so, yeah, the YNAP0 gives you a list of the commands that we need. So this is going to be very similar for the diabetes data. So you might take a look at it. Remember to write up your answers when you're finished. Okay, so let's take a look at the last example. Maybe I'll pause this time so you don't have to watch me delete everything. Okay, so now we're on to problem 3. And problem 3 we're going to be doing clustering um, to get the centers. And so we're going to be doing the regression problem. And so I'm giving you the EDM matrix as well. EDM stands for Euclidean distance matrix. And so we'll use that to compute our distance between points. And so let's see how we're going to do that. Let's put those two files into Octave. And now let's take a look, see what we have here. So EDM, when you do this, you're going to have two matrices. So think of W as the set of centers and P as the set of data. And so they should be number of points by dimension each one. And so what you get out then is the number of points or number of centers by the number of data points, right? That's a matrix that's number of centers by number of data points. And so this matrix or this function will compute that. So let's see what we have in our RBF regression. So first we create a set of data, just a simple set of data. This is one-dimensional data. And then we split it into training and testing sets. And so I'm doing this live instead of using the built-in command. So you can also use the built-in command from the other problem if you want. And then we just do the k-means. Oops, do I see a problem here? I sure do. I should be using the training data for my k-means. Good, so I was actually using the whole thing, so I might have gotten a better result than I meant to have. So here's the default spread for the k-means, and then I'm going to take a look at the D here, line 25. That's the line or the distance matrix between the centers and the data. And then line 26, you're just constructing what we're calling the design matrix, right? So that's phi of the distance matrix, which is the exponential of minus the spread times d squared. D is a matrix, right? Okay, and then line 27, we're just looking at the size of phi because we're going to be adding a row to phi. Remember how we're doing that? So we add a row at the bottom of phi and a column to the side of W. Actually, the column's going to be there for W hat, right? And then we do some prediction on new data. And then we do some plotting. So let's take a look and see if this works. I'll just hit the run. Oop, am I going to have to give it more time? Whoops. K-means undefined. Oh, you know what it is? I didn't do the package, load package statistics. So let's go ahead and do that. Isn't that what it said to do? Oh, package load. There we go. Good. Now we'll run our code again. Clear CLC CLC and run. Oh, beautiful. All right, so we're getting very much the same kind of results that I had before. And so you can read the legend here. Notice that the data points that are the centers are evenly spaced between 0 and 1, which is what we would expect. We would expect the centers to be, or the centroids of the data to be evenly spread out through the data. Good. And then we have, so we just fixed the number of centers to be 4 in this case, and we got some very nice results. Good. Notice we didn't get any, I guess we didn't get any samples out here on the end, but everything else is looking pretty good. All right, and so we're going to try to do this regression problem with some other data. In fact, I believe we're not actually doing regression, are we? Let me pause for a second. Okay, so I was just double checking the problems. Problem one is doing the linear network for classification. We now have our examples running in Octave. This problem two is to use orthogonal least squares to do the clustering on the Pima Indian database, the diabetes database, diabetes database. Let's see if I can say that. And then finally, we're doing the RBF experiment using clustering. And so the clustering we're actually going to be doing, or the data we're going to be doing, is actually a classification problem with hand digits. Remember we did that before? Um, and so my example is just to show you how to use the clustering to find the centers. But you'll have to change the code because this is actually a clustering problem and not a regression problem. So that's not a big change. But if you do have questions, let me know. Um, yeah, so that's it for the Matlab version. In the next version, we'll take a look at the Python files.